That's his velocity, right? Goes like that, at a certain angle theta. After you complete this triangle here, that'll be x, and that'll be y. Okay? So management of xy in what we call Newtonian mechanics is a fixed frame of reference. It's inertially fixed. Okay? And now we introduce the following two parameters. VR vector will be VR positive along J, and that's basically the current, the water current. You know, so many miles per hour or whatever, okay? And notice basically it's directed along the y-axis, okay? So a certain current in this river that's going towards the north, and the magnitude is VR, okay? Vs is going to be the velocity of the swimmer relative to the river, right? Right? Because what's happening basically is we're saying here he is over here, and he's going to be judging his desired orientation relative to the water that he's in, which is flowing. So therefore, we're going to basically say Vs is over here, and that's the velocity of the swimmer relative to the river. Okay. So there's really nothing to do with VR. We'll just keep it as VRJ. And what we're going to do over here is write this vector Vs as what? Its magnitude times a unit vector along the direction. Now be very careful, right? If I do cos theta I plus sine theta j, that's a unit vector from the origin to that point. I want to go the opposite, right? So I need a negative on that. So I need negative cos theta I, negative sine theta j. Okay? That's a unit vector from xy towards the origin. So we can write Vs basically as minus Vs. And just from the diagram, what's cosine theta? It's x over the square root of x squared plus y squared, right? And the sine is y over the square root of x squared plus y squared. Okay. Now what we're going to do is, what happens when I add VR and I add Vs? What's the net of VR Vs? That will be the velocity of the swimmer relative to the fixed frame, right? And we know what that is, right? So the velocity of the swimmer is dx dt I plus dy dt j, right? That's basically his velocity vector relative to this fixed xy frame. And that's just the sum of the vector VR, which is the river, plus Vs, which is the velocity of the swimmer relative to the river. So if I take the velocity of the river, VR, and I add to it the velocity of the swimmer relative to the river, what do I get? I get the velocity of the swimmer relative to the xy frame. Okay. Okay, let's just add these all up. I get, I think I forgot some unit vectors here, right? I, J. Okay. VR is along J. Okay, so VR plus Vs. What do I get along the I direction? I get two guys, right? Let me just write this out to you. Vs x minus Vsx over the square root of x squared plus y squared, right? That's the I component, and there's no I component on there, so that's basically I. Okay? And then along J, I get plus velocity of the river over there, right? I get a VR along J. And from here, I pick up a minus Vsy over the square root of x squared plus y squared. Okay. Let me just check that J component again. I got I'm doing things too fast over here. Let me just see. VR plus VS along I. What do I have? Okay, that's nothing. I got this guy along I minus VSX over the square root, right? That's okay. Then along J, I got VR along J. Yeah, there's a mistake. That's not right. Right? I got the velocity of the river along J. And from here, along J, I pick up a minus VSY over the square root. I'm spelling in the wrong place. Check. Okay? So we have two equations now, right? The derivative of x with respect to t is equal to minus VSX over the square root of x squared plus y squared, right? Okay, and dy dt would be VR minus VSY over the square root of x squared plus y squared. Okay. Now I want to find his trajectory, which is mean what? It would be nice if I had dy dx, right? Because then I can get the curve. This tells us actually if we integrated these, we could actually get the velocity. This gives us the velocity components, and if we integrate them, we get the xy position as a function of time, parameterized. But I want to know just, although that would be interesting to do, I'm really just interested in the curve, right? Y versus x. So from the chain rule, dy dx is just dy dt divided by dx dt. Okay? So for dy dt, I got VR minus VSY. Checking out my algebra, right? I say dy dt, VR minus VSY over the square root of x squared plus y squared. Let's say x squared plus y squared to the minus 1/2. Right? Y dot. VR minus VSY over the square root. And downstairs I have dx dt, which is minus VSX over the square root of x squared plus y squared. Okay. And now we can just simplify this, multiply through by the square root of x squared plus y squared, okay, and do the ratio, and it'll follow directly from there that you can get dy dx is equal to y. Remember, we have a double negative over here. K, the square root of x squared plus y squared divided by x. And the important parameter here, this always happens in these physical problems, this k is the ratio of the velocity of the river to the velocity of the swimmer relative to the river. Okay. Very interesting how it's parameterized in terms of this. And again, just qualitatively, if VR was much, much bigger than VS, means K is, is a large number, what's going to happen? It'll start off over here, and the current will just be overwhelming. It'll probably go over here, and it'll go, keep going north all the way, never reach it. And there's some critical value of that ratio where he'll actually just reach this point, and what happens in between, it's going to be an interesting thing to look at, okay? But basically what you have to do is you have to solve this differential equation now, okay? So, okay, let's see, we may have to continue this the next time. Okay, what I'm going to do now is what you would recognize if you cross multiply that it's homogeneous same degree. Right, you got an x dy, and the dx coefficient is also polynomial homogeneous of degree 1. So we could write this as dy dx is equal to y over x minus k, the square root of 1 plus y squared over x squared. This ratio y over x basically is what's going on over here. Okay? So you know what we do over here. We're going to say let u equal yx. let u equal y over x, or y equals x u. Okay? So that'll make it everything in terms of u now. Okay, what's dy dx? X du dx plus u, right? Y is equal to xu, so therefore dy equals xu prime plus u times 1. That's y over x, which is u. We always get that cancellation. Minus k, the square root of 1 plus y squared over x squared, which is u squared. U is knocked out. Okay? So I get du dx is equal to minus k, the square root of 1 plus u squared divided by x. Okay, it's variable separable, right? So that becomes the differential of u, the square root of 1 plus u squared, equals minus k over x dx. Okay, I think I'm going to cut out some steps because we're going to lose some time over here. Okay, let me just outline. If anyone wants the details, I can write it up. Basically, get to this point over here, right? Du over square plus u squared minus k over x dx. You integrate. To do that integral over there, you have to make a trig substitution. Okay, right? Let something like u is tangent theta. Okay, and when you integrate and use the initial conditions, we know that when x equals 1, y equals 0, let me just tell you what you get. I'll put little dots over there. The solution at the end comes out to be 1/2, this is interesting, x to the 1 minus k minus x to the power of 1 plus k. Okay, but k is that ratio, VR to vs. And now we can basically summarize what's going to happen. Okay? Suppose k is equal to 1. That's the critical value, right? When k equals 1, y is equal to 1/2. Let's plug in k equal to 1. 1 minus x squared. Right? So with that condition then, when he reaches x equal to 0, you plug in x equal to 0, y of 0 is equal to 1/2. So what happens basically, when VR equals Vs, that is when the velocity of the river and the velocity of swimmer relative to the river are exactly the same, they'll start over here, and what will happen is it'll land up north by 1/2 mile, whatever the units are. Okay? He doesn't get to his desired destination. He gets to the other shore, but he overshoots it because the river has pushed him up over there. Okay. And then, this all makes physical sense. Suppose k is greater than 1. K is greater than 1. That means, remember what k is. It's VR over Vs. So k is bigger than 1. That means the velocity of the river is going to be bigger than the velocity of the swimmer relative to the river. The current is probably just going to be taking him off to infinity. And you can see what happens over there. For k greater than 1, what's y at x equal to 0? Okay, you come back over here. You plug in k, was it bigger than 1? Okay, that goes to 0. But now, when k is bigger than 1, it's x to a negative power, and that goes to infinity. Okay, so the graph over there now, he's going to come over here, and then rather than land up north over there on the other shore, he's going to come here, and it's just going to go asymptote to there. And that's what we expect over there. And then finally, here's something that's interesting. If 0 less than k less than 1, plug in k between 0 and 1, that goes to 0, that goes to 0. Y of 0 equals 0. So what's interesting is that there's this range of values of k, namely, k obviously is positive, right? But k less than 1, he'll reach his desired destination. Okay, he'll get a curve that will be exactly like this. Now remember, there won't be a unique one depending on the value of k. I'm going to show you, for example, k equals 0.5, k equals 0.6. Maybe one will go like this, and one will look a little higher, but it'll always reach the origin. Okay? And we know for the case of 0, he should land up over here. And for k greater than 1, we'll have some other fancy curve that asymptotes. So let me just show you that, and then that'll be it for today. Yeah. Okay. Again, I urge you to work out the details of this, okay?
I did earlier.
Oh, okay. Let's start again. Okay.
God, Kevin, we were running from the board for like 20, 30 minutes.
Gosh, Kevin, could you?
Sorry,
Sorry,
it's okay, it'll take a few minutes.
Sorry. I'm doing that out loud.
Exactly, Kevin. You're why we can't have nice things.
It's taking like 30 whole seconds. Oh.
Kevin, you're why we can't have nice things.
You're why we can't have nice things. I'm why we can't have nice things. Can't you see the constant fighting is tearing this family apart?
What is that from?
Okay, okay. So, what I've done over here, we put arrows on it. Okay, so the swimmer, remember, starts at this point over here. That's that east shore. He's swimming over here, always directing himself towards the origin. And we found that the solution was critically dependent on this ratio, VR to VS, where VR was the speed of the river, and VS was the speed of the swimmer relative to the river. Okay. So the first case we did was when it equals 1, right? And that was, remember, K was this ratio over here, the blue curve. And indeed, you see how the blue curve starts off over there, and it reaches 0.5, right? So he's reached his destination, but he's too far north, okay? Then, let's look at this orange one over here. VR over VS equals 1.2. According to our analysis, it can go to infinity. So what happens, he starts off over here. Remember, the current is very high relative to him, so it takes him off, and he just asymptotes. Yeah, he never even reaches the other shore. And then finally, the green and the orange are two cases where VR or VS, or the K parameter that we had, lie between 0 and 1. I guess one is 0.75 and one is 0.25, okay? And it makes sense, right? The 0.25, which is less, means that the swimmer really is gaining on the river, so it's almost like a straight line, right?